Okay, now that we've talked about eigenvalues and eigenvectors and how to find them, what they are, uh, let me go through a few facts about eigenvalues and eigenvectors. But even before that, I want to clear something or make something clear because every so often a student will try this. Up here at the top is the proper way to find the eigenvalues of A. You construct the matrix A minus lambda I, and then that's what you find the determinant of and do row operations for. When you find the null space. But anyway, if you did it the proper way, you would get the eigenvalues 0 and 3. If you do row operations on A first, in this case, you get this. You get a row of all zeros, because that's the way A is constructed in this case. And then find the eigenvalues. A minus lambda I would be this, and you get the eigenvalues of 0 and 2, not 0 and 3, which are the correct eigenvalues. Row operations do not maintain eigenvalues. So don't do your row ops on A too soon. It's a little fact. The determinant of this A minus lambda I is going to factor, right, like this, because these lambdas with subscripts are the eigenvalues. So this thing's going to turn into this polynomial like this that can be factored this way. But look what happens if I set lambda equal to 0 on both sides. I get the determinant is the product of the eigenvalues. There you go. That seems like a pretty cool fact. The determinant of A, not the determinant of A minus lambda I. The determinant of the original matrix A is the product of its eigenvalues. Let's see. I just said the determinant of A minus lambda I. This thing should have a name. I keep referring to it, but to my knowledge, it does not have a name. Like I said, it's a polynomial in lambda, so it can be written this way. And without proof, I'm going to say that this could be broken down this way. These are the eigenvalues, right? Now here is the determinant of A minus lambda I spelled out more explicitly. And it could be broken out this way. Again, kind of take my word for that part of it. I'm going to do that without proofs. But if you compare these terms, the minus lambda to the n minus 1 terms, it says the sum of the eigenvalues equals the sum of the main diagonals of A. That sum is called the trace of A, the sum of the main diagonals. So that's another fact that seemed kind of cool, kind of nifty. The sum of the eigenvalues is the trace of A. The product of the eigenvalues was the determinant of A. What if I just add the same constant to every main diagonal of a matrix? So I'm doing this to A, and I get another matrix B. Look what happens when you find the determinant of B. I mean, B minus lambda I. When you try to, we're looking for the eigenvalues of B. So we set up this determinant of B minus lambda I, which means this. And if I call these terms just lambda A's, where lambda A equals lambda B minus K, you see that the eigenvalues of B are the eigenvalues of A plus that constant. So adding a constant to all the diagonal, the same constant, adding the same constant to all the diagonal elements of A simply adds that constant to the eigenvalues of A. One more little fact to prove. The eigenvalues of a to the n. First, let's just do a squared. If I do a squared times k, I can break it up this way. A squared, A is a square matrix. That means a squared means a times a. By the associative property, I can do this. But a times k equals lambda k. I can pull that out. And ak again equals lambda k. I get lambda squared k. I could keep on doing this, or by induction, a to the n, an integer power, times k is lambda to the n times k, which means this. The eigenvalues of a to the n are just the eigenvalues to the nth power, the original A matrix. Every eigenvector of A is also an eigenvector of A to the n. Okay, next subject will be diagonalization, and I'll save that for another video.